Okay, so now I want to talk about how to interpret, or give some examples of how to interpret SQL statements sort of in terms of relational algebra. We're not going to actually write out the plans, but I want to give you some experience staring at what may seem sort of complicated and kind of teasing out what's actually going on here. And so for people that have spent a lot of time around databases and SQL, these may or may not seem particularly complicated, but if you're just starting out, they probably do. So in this first example, what do we see here? Well, what you want to look for when you're sort of staring at something that may seem sort of hairy is, look for the from clause here. And so in this case, it's a little funny, right? Because we see that the from clause does not have a table mentioned, it has a nested query within it. And we remember that that's perfectly fine because of this closure property of the underlying algebra. We know that any relational algebra expression, and therefore any SQL statement, is going to return a table. And it operates on tables. So if you can operate on if you operate on tables and you return a table, then you can sort of chain these operations together and you have this nice closure property. So we know that we're allowed to query derived results just like we're allowed to query base tables. Okay, and so in this case we're doing a derived result. Now, so let's go down to the other from clause. Well, here we see another nested query, another layer of nesting, again, perfectly fine. And one more layer down we see this table here. And so where this data came from was a sensor that was mounted underneath a oceanographic research vessel that was collecting measurements of a variety of different variables. Here a few of them are mentioned: fluorescence, oxygen, nitrates, and there's several more. And then this is latitude and longitude where the ship actually was located at that point in time. And they're also tagged with this timestamp. So they're tagged with latitude, longitude, timestamp, and a bunch of measured variables. And so what this operation is actually doing is aggregating, binning these measurements onto 5-minute windows. Okay, and so we can see how that's done. So in this inner query, there's some work you call this function to cast the timestamp to a float. That's not particularly important. And here we see this trick where we just use a constant value right there in the select clause. And so what that does is sort of append a new column with a value 5 for every record. Okay, and I'll say maybe why this was done in this particular case in a moment. And then in the next layer up, we see this kind of hairy expression involving bin size twice. And what it's doing is rounding down the timestamp to the nearest 5-minute window. Okay, so 6 minutes and 32 seconds becomes 5 minutes, and 11 minutes and 29 seconds becomes 10 minutes, and so on. Okay. And then in both cases, by the way, we see the star here, meaning that all other columns are going to be passed through. And then finally, in the outer query, we have bin ID, which we computed here. Notice that we've got this renaming operator where we can have this complicated expression and just give it a nice, convenient name. So we got that passed through, and then we compute the average of these other values, the average latitude and the average longitude within that 5-minute window as well. Okay. So given that we're doing an average, we should expect to see a group by, and in fact we do. We're grouping on the bin ID, which would make sense. And then we happen to be sorting by bin ID just to make sure that the records come out in timestamp order, because perhaps some application requires it that way. Okay, so why is this sort of overly complicated? Why not just collapse all this into one expression? Well, you could, but it's for the same reason that you might sort of abstract things or refactor things in an imperative language. There's a little bit of software engineering being applied here so that this complicated expression can be reused in multiple places. In this case, it's only being used once, so you could perhaps move it there. But it sort of separates two different blocks of logic. Okay, so in this slide, I've color-coded the 3 different blocks of logic, red, blue, and green, so you can see the layers of nesting. But the main thing I want you to take away is that one is that nesting is perfectly fine, and you may see it, and not to worry when you see it being used in practice. And second, just to kind of convey that as you start to do more and more analysis in SQL, more complicated analysis, there are ways to kind of refactor the complicated queries so they don't necessarily look so complicated. Another thing you could do here that we will talk about in perhaps the next segment is save this result as a view, right? Give it a name, and then you could refer to it in the outer query just as a table. Okay, and I'll talk more about that next time. But these are some of the tricks you can play when you're sort of working with in SQL. And in fact, some of the things you may see people do, even if you're not planning on doing as much SQL authoring yourself. Okay. Fine. So here's another example. Same thing. The first step is to look at the from clause and see what you see. And here we see two tables, and there's this keyword inner joins. Now the join is explicit, and the join condition here is this, where we have some sort of ID and some sort of other ID. By the way, one of the other things I want to kind of do here is to show that you can kind of analyze the structure of a SQL statement to understand what's going on, even if you really have no idea what the data is all about. And in fact, it's kind of helpful to do so. This is something you'll be presented with in a data science context, as someone will say, look, we need to predict what the average sales for next month is going to be. And you say, okay, great, give me the data. And they'll say, well, I don't know, it's in some database over there. Right? And you'll go over there and talk to the DBA, or maybe there won't even be a DBA, and you'll have to sort of analyze what's going on inside that database on your own. And so that means staring at the schema, which we haven't done, but it also means staring at certain people at queries, which you may not have written. Okay, so having a little bit of a skill of analyzing these complicated queries can be important. Okay, so fine. So this looks ostensibly like the join condition, but if you look at the where clause, I want to make sort of a point here that the table referred to as X, this hotspot deserts, and the table referred to as W are involved in additional conditions down here. Okay, and so these are actually join conditions as well, right? Even though this one was explicitly listed as on, an inner join on this particular condition, anything that involves, anything that applies a condition to attributes that are in both tables, right? Any sort of condition involving attributes from both tables is a join condition. And so this whole thing is actually one sort of complicated join condition. All right. So I went a little bit out of order into a little bit different than the order I wanted to go in, but let me backtrack and come back to that. So hold that thought. Popping back up to the top, this other piece of complicated logic here. Well, this is a particular syntax that's available in SQL called, a case statement, and it acts about the same way as a case statement in other languages. So that's not too bad. But in particular, even if you just ignore all this logic, you can just collapse all this down and say, well, look, there's some function that's computing lin overlap. And where did I get that name? Well, that's what they name the result of this complicated expression, the length of the overlap. And in fact, I happen to know a little bit about where this query came from. What they're working on is genetic sequences, and you may be able to deduce that if you just stare at this. There's SNP region, which stands for single nucleotide polymorphism, and there's strain that may give you a hint, and BP is base pair, and non-coding regions, non-coding positions gives you a bit of a hint if you've done any work in bioinformatics. But if you haven't, that's okay. The point is, length of overlap appears to be the name of this thing, so it's almost like there exists a function, length overlap, that involves these attributes, and we don't even care what's inside it. It's just a function. So that helps us sort of see the underlying simplicity of this query in this case. Okay. Then back to this other complicated expression. Let me show you a little about what's going on here, just because I think it's kind of a fun example. If you break these out into these three conditions, and you happen to know something about where this data is coming from, you can see that what this is saying is, well, look, we want the start base pair from the X table to be greater than the start base pair from the W table, and we want the end base pair from the X table to be less than the end base pair from the W. So it's this picture, right? We want the blue X interval, right? It's a sequence. The X table is filled with ranges, right? Start and end ranges, intervals, and the blue interval needs to be completely contained within the red interval, or the red interval needs to be completely contained within the blue interval, or the red interval needs to straddle the X start base pair, which you can do if you stare at this condition. Okay, so they're doing kind of an interval logic right there in SQL. And so the point of maybe looking at this in enough detail to try to understand what's going on is a couple of things. One is this point about the join condition is that it's not, even if you don't understand what's going on, you can sort of see the structural details to understand that it's just a join condition, but also that you can actually do certain kinds of analytics directly in SQL. This is a fairly non-trivial operation to do that many people, especially among people who have either not had good experience with databases or have heard from their friends who have not had good experience with databases, that this would be something that's considered sort of impossible. And it's not impossible, and nor is it really even a bad idea. It's actually kind of a natural thing to do. And so analytics in the database should be a part of your bag of tricks. The first step should not be let's pull everything out of the database and then start using imperative code. Okay. This example alone, I would hope, doesn't convince you of that claim I just made of getting things out of the database is a good idea. But there's going to be a sequence of arguments that I make probably throughout the quarter here and there. Okay. Meanwhile, I should put the caveat that this is not, I'm not going to be pushing databases as the ultimate solution to data science, but by any stretch of the imagination. But there is a role for it to play. Okay. All right, and so now with these, we collapsed this into one function. We can also collapse the join condition into these two things. It must match on this CHR field, and then it must have this kind of overlaps condition be true that we saw on the last slide. And so this is just an example of a theta join, where there's some non-trivial function being applied on each pair of tuples. Okay. Let me stop there and pick up on user-defined functions next time.